Welcome back to ECE 442-542. Homework number 1, I've been seeing a few people in my office hours, and so I'm guessing a few of you have started. That's due on Friday. And there is a sample MATLAB write-up for one of the parts, meaning you have 25% of your answer already provided to you, but I've had a few emails from students saying, how do you want us to write up these MATLAB exercises? And I hope it's not that difficult. Basically, you're just copying the code that I've already produced or given to you, but it's to try to get us up and running, or at least walking, relative to some MATLAB material during the course of the semester. Homework 2 will be due a week from Friday, and exam number 1 is 2 weeks from today. Just as a reminder, just to get you awake right now. Oh no, 2 weeks. So now you're stimulated for the next 5 minutes before you pass out again, but hopefully you can pay attention to at least the goals that we're trying to cover for today. What I want to do is talk about this complex variable z. How can we interpret that? Can we relate that to something we already know about? And that's something that we already know about is the Laplace transform. We will talk then about, once we have this relationship between s and z, they're both complex variables or complex numbers, we'll talk about this mapping from the s-plane into the z-plane. If you know something about what happens with pole locations in the s-plane, then mapping those into the z-plane, you'll be able to maybe understand a little bit about what these regions in the z-plane correspond to. Then we will give an example of sampling frequency. We'll derive a sampling period, capital T, based on some closed loop bandwidth. We'll go through an example of time domain to frequency domain, meaning starting with now a difference equation. How do we get that into a transfer function or a frequency domain representation of the same system? We want to become comfortable doing that for discrete time systems. Then we will jump into z transforms. Once we have talked a little bit about this variable z, then let's now get into the z transform. We'll define it, and then we will go through deriving or developing some of these z transforms of common waveforms, where the common waveform now might be the pulse input, it might be a unit step, it might be an exponential, it might be an exponentially damped sine and cosine. What does that look like, or what does the z transform of those time domain waveforms, what do they look like? Let's start then today with this z variable. How do we gain some insight into what z is? And I want to start with what we're already familiar with, which is the Laplace transform. I had some students come in today wanting to add the class, and they said, oh, we finished 220, so we're ready to go. I said, maybe not. Have you had Laplace? No. Okay, then you're not ready to start with 442. We're at least assuming that you've had some Laplace transform. Actually, you're an expert with Laplace transforms to get you to this location. If that's the case, then you should be able to, if I said, okay, here's a time domain signal, let's call it x of t, then if I wanted you to take that into the frequency domain, by means of the Laplace transform, what is the Laplace transform definition of a generic signal, little x of t? Let's say the one-sided Laplace transform. you remember what that is? What's the definition of the Laplace transform? Is it a differential equation? No. What is it? It's some integral, isn't it? It's an integral, and you're integrating x of t over all time to produce some frequency domain. You're collapsing all of this time domain information from the x waveform, the x of t waveform, into a frequency domain object. You're doing that by integrating. We're saying this is a one-sided x of t, meaning it's valid from 0 up to infinity, and that infinity is sort of hiding there with the y. I don't know why I made my y have such a long tail. Maybe I'll shorten the tail on that. This is now x of t, e to the minus st dt. That now incorporates all of this time domain waveform over all time into a frequency domain quantity. Now, what happens if in the time domain we actually delay that signal? It's the same x of t, it's just delayed an amount t sub 0. What does its Laplace transform look like if capital X of s is the Laplace transform of little x of t? Do you remember what happens to the Laplace transform? Is capital X of s anywhere? Is it present? You could actually do this in your head and just start doing the substitute little x of t minus t naught into the definition of the Laplace transform and derive this relationship. Maybe that's what you should do while you're watching the game tonight, okay? Because it may not be much of a game, and you may want to get more out of this, right? This may be more entertaining, deriving this relationship. I'm going to trip over this table. Be an unstable system. How's that? This now becomes e to the minus t sub 0 s capital X of s. The impact of this delay in the time domain becomes a weighting of capital X of s by this scaling factor, which is a complex exponential. E to the minus t sub 0 is the amount of the delay in a unit of seconds. S is the complex frequency variable. But that's the relationship. If you delay your time domain waveform by an amount t sub 0, that's equivalent in the frequency domain to scaling by e to the minus t sub 0 s. Let's now use that to our benefit. If the delay, if t sub 0 is equal to one sample period, the time t sub 0 is actually capital T, is what we're going to use. If t sub 0 is one sample period in duration, then a one sample period delay in discrete times frequency domain, how were we defining that? Or how were we representing a delay of 1 unit in the frequency domain using z's? That was this z to the minus 1, wasn't it? So z to the minus 1 represented in the frequency domain for a discrete time system the amount of a one sample period delay. If we compare that with the S domain representation of a delay, then z to the minus 1 would equal e to the minus t sub 0 s, if t sub 0 represents one sample period. If we're sampling at 10 milliseconds, 0.01 seconds, then t sub 0 is 0.01. And we would just put in e to the minus 0.01 s is equal to z to the minus 1. That's actually giving us the relationship between z as a complex number and s as a complex number, where t, capital T, is the sample period. If z inverse is e to the minus ts, what is z? We're just changing the exponent, aren't we? We're changing the sign. This is now e to the ts or e to the st, and I'll probably use it e to the st because we will be replacing s with some location in the complex s-plane, meaning an advance of one sample period, which is really just this complex variable z, corresponds to e to the st, an advance of capital T units of time in the s domain. This that I've boxed is the definition of z in terms of s. Meaning if s is a complex number, let's just think of a point in the complex s-plane. Minus 3 plus j2, that's s. You can substitute that value of s into this right-hand side. If you have a sample period, capital T, that's going to produce a complex number z. And we'll work through that. But first, let's just remind ourselves, make the following statement. Z is a complex number that we will use as a frequency domain operator for discrete time systems. Just like we had this s as an operator for continuous time systems, if we multiplied something by s in the frequency domain, what did that correspond to in the time domain? If you saw an s operating on something in the frequency domain, let's say a capital X of s, what did that correspond to if you went back into the time domain? S capital X of s was what in the time domain? A derivative of little x of t. If you wanted to integrate in the time domain, that was like multiplication of s to the minus 1 or 1 over s in the frequency domain. Now we're thinking about z being an operator for discrete time systems. If we multiply by z, that's like an advance of one time step or one sample period. A multiplication by z to the minus 1 is like a delay of one sample period. Let's now just look at what happens relative to this S-plane to Z-plane mapping. trying to build up some insight into what's happening in the z-plane. We're now going from one plane, which is complex, to another plane, which is also complex. Here, let's say this is the real part of our s variable. This is the imaginary part of the s. So this is our s-plane. This will be our z-plane. This will be the real part of z. This will be the imaginary part of z. What we may learn is we might actually want to be more in polar coordinates in the z-plane versus rectangular coordinates in the s-plane. But we'll work through that in a little bit. What we are interested in is if we now had a point let's say at -3 plus j2, how does that now map over into the z-plane? And we've just learned, or we just said, that z is e to the st. What's that going to look like? Where's that pole going to end up in the z-plane? So now we have s equal to, let's say, minus sigma plus j omega sub d in more general terms. And we had our specific point as -3 plus j2. Just to give us something to work with, let's assume that our sampling period, capital T, is 0.04 seconds. And we may derive where that comes from in a minute. But for now, let's just say it's 0.04. What does z look like? Or where does z end up? We know the relationship that is relating z with s. This is now e to the minus sigma plus j omega sub d times t. That's e to the st. And we can write that, we can distribute that sample period across both terms in the exponent. And we now have e to the minus sigma t plus j omega sub dt, but we could also write that as e to the minus sigma t times e to the j omega sub dt. And this now looks like some magnitude, some value in a, let's say, a polar form number, and this is some angle theta sub d, meaning we now have an r e to the j theta sub d, where r is equal to e to the minus sigma t, and theta sub d is equal to omega sub dt. Keep in mind that that theta sub d is not the same as we've been talking about if you took 441, the theta that we kept looking at in the s-plane. So don't make that connection now that I've told you about it. It's now just theta sub d. It's a new value. Let's see what that looks like for our particular example that we started with. For our example, we had s equal to -3 plus j2, and t is equal to 0.04. So that now z is equal to e to the minus 3 plus j2 times 0.04, or this is now e to the minus 3 times 0.04, and e to the j is running out of room, so let me just do the multiplication. 2 times 0.04. We now have z is equal to e to the minus 0.12 e to the j 0.08. What you have to keep track of now, this is just some value, r. This 0.08 is an angle in radians. And you can convert between radians and degrees if you wanted to put that into a degree value. 0.08 in radians isn't very big. It's actually going to be, r now becomes 0.887, and in degrees this becomes 4.58 degrees. Can you plot that in a complex plane? You've done polar numbers in 220, so maybe I shouldn't have discounted 220 so much, at the beginning of class. This is now a value, a magnitude of 0.887 at an angle of 4.58 degrees. You can see that in a complex plane. We've now mapped minus 3 plus j2 in the s-plane. Here's, let's say, 1. Now we've gone, and this won't be a very accurate angle, but this is now, let's say, some angle of 4.58 degrees, and this length is 0.887, and this is now where the z value ends up in the z-plane when we mapped from minus 3 plus j2. What else did we have to assume? A sample period, capital T, in order to get us those particular numerical values. Questions on that? How we went from the s-plane the s-plane over to this point in the z-plane, a radial distance of 0.9 roughly at an angle of 4.5 degrees. All we needed to know was this sampling period, capital T, and where we started in the s-plane, and we can do the math. It's just some complex numbers to get us to that particular point. What can we say about that particular pole and, let's say, the original pole? The pole in the s-plane, can we say anything about it? And if that corresponded to a system pole, if it was a system that had a pole at minus 3 plus j2, can you tell me anything about the behavior of that system? It's stable, isn't it? It's in the left half plane. It has an e to the minus 3t. It's decaying at e to the minus 3t. What can you tell me about that, the stability of the pole in the z-plane? Radially, its magnitude is less than 1, isn't it? It has a value of 0.887. That's less than 1, so it's also collapsing. Good. We're consistent. We have stable in the s-plane, we have stable in the z-plane. Let's make some other observations relative to this s-plane and z-plane mapping. One is that r equal to e to the minus 3t was less than 1. And the key thing is that negative number in the exponent. If we actually were thinking about this, let's say this is now the real value of s, let's just call that x, and this is 1, this is 2, this is -1, this is -2, -3. Do you remember what the exponential curve looks like? E to the x as a function of x. What is e to the 0? That's 1. So we would be right here if this was zero. What is e to the 1? E. What's e? 2.7 something. So that's a little ways up here, isn't it? E to the 2. 2.7 squared. Maybe it's not quite 9, but that's quite a ways up here, isn't it? And so I'm not going to be able to do this very well. What's e to the -1? 0.37, right? That's where it gets to after one time constant. So now we're down here at about 0.37. E to the -2 is less. So this is our shape. That's e to the x. That's our exponential shape. And what can we say relative to, we would like e to the x always to be, if it's stable, less than 1. That's going to happen as long as our real value of s is negative. And that's what this curve is trying to maybe show you. Here is our negative exponent. Meaning if you have points that are in the complex s-plane in the right half plane, they're going to have a real part that's positive. They are going to be mapped to locations outside the unit circle. Their radius is going to be bigger than 1. That's one observation. Meaning values of s in the left half s-plane map to values of z inside the unit circle. Relative to this mapping, we also see that theta sub d is just omega sub dt, and that's just some angle. So we have some radius at an angle. That third observation is theta sub d is omega sub dt, meaning if you know the imaginary component or imaginary part of your complex number in the s-plane, you multiply that by the sample period and you have your angle theta sub d in the z-plane. Question? So the question was, is there any significance to theta sub d? Even though it may not tell us anything about stability, what does it tell us? Let me just sketch something. We know we have an r. That's the radial distance away from the origin if this is our z-plane. And here is theta sub d, which is omega sub dt. Let's just think this through. Suppose r is 1. What's going to happen if we continue to iterate with something that has an r value of 1? Is it going to collapse or expand? If r is 1. It's on the unit circle. Let's say we have a pole on the unit circle. What's going to happen as time evolves? If we raise r to the first power, what happens? What happens to r if it has a magnitude of 1? 1 to the 1 is 1, right? 1 squared, 1. 1 cubed, 1. It's not growing or contracting, is it? But what happens to the angle? If we were at 45 degrees, now we square it, where do we go? 90. We 3 times that, we go to 135. 4 times, 180. So that's telling us how we are oscillating in the time domain. We're staying at a magnitude of 1, but the angle theta sub d basically tells us how many times do you or how many points do you have in each oscillation. If theta sub d was 45 degrees, you would have 8 points in that one cycle of oscillation. If theta sub d was 22.5, divide 8 or multiply 8 by 2, and now you have 16 points in one cycle of oscillation. So that's what the theta sub d tells you. It tells you sort of how many points are you going to see in one cycle of oscillation. Meaning in that 4.5, we're going to see a lot of points, aren't we? In that oscillation, one cycle of oscillation. And since it was 0.887, it's going to be collapsing as it's oscillating. Does that help answer your question as far as what theta sub d corresponds to, or how you can maybe think of theta sub d? Let's now make one more observation, and that's relative to this rule of thumb that I've continued to talk about, and that is, where does this capital T come from? What's our sample period? If you're able to pick it, you want to pick or select capital T, the sample period, to be 30 times the closed loop bandwidth. Let's just look at an example. Suppose that somebody says, suppose we want a closed loop bandwidth of 5 radians per second. Or the notation that I've been using, I think, is omega sub c is 5 radians per second. Then what's our sample period, capital T? And I think you can guess what that's going to be based on what I said we might get back to after we started one of the earlier examples. But where did that 0.04 come from? Omega sub s is our sampling frequency in radians per second. We said that's, or you can relate that to the sampling frequency in hertz by this relationship. Omega is 2 pi f. This is now the sampling frequency I'm having trouble with my y's. I don't know why. All right. Had to wake you up because, never mind. This is now in cycles per second, or in hertz. But we know the relationship between f in hertz and the sample period. They're reciprocally related. So this is now 2 pi over capital T. This is our sample period where f sub s is 1 over t. But we said we wanted this sampling frequency to be a factor of 30 bigger than the closed loop bandwidth omega sub c. That's just a rule of thumb. If you don't remember anything more from this class and somebody says, oh, your closed loop bandwidth is 5, and they say, how fast should we sample? You might say, oh, well, let's go 30 times that bandwidth. That now says that we're sampling omega sub s is now 30 times 5, so that now we can solve for capital T. Capital T is now, if we multiply both sides by t in this relationship of 2 pi over t equal to 150, we now have 2 pi over that 150, which we can sort of play fast and loose with pi. Since we want t to be smaller rather than larger, we can sort of approximate 3.14159 by 3. That's okay. So t now is approximately, or it's 2 pi over 150 if it's 30 times the bandwidth. This is now t is now 2 over 50, or depending on how you wanted to think of this, we can multiply both sides, top and bottom, by 2, so that we now have 0.04. So that our sample period t is 0.4 seconds, or 40 milliseconds. And what is the sampling frequency in hertz? Well, that's just 1 over t. Or now we're sampling at 25 hertz. That's what that capital T of 0.04 corresponds to. We're sampling at 25 hertz when we had a closed loop bandwidth of 5 radians per second. Questions on that? This relationship between S and Z? Yes? So now what's the advantage? The question was, what's the advantage of having 30 oscillations, or 30 samples per oscillation? Is that what the question was? Now you've possibly heard of the Nyquist frequency. Have you not? And what's the Nyquist? Double. So you say, oh, I want to sample at twice the highest frequency. That's so you can preserve the information content. This is a controls class. So we want to maybe see more of the shape of the waveform, and it may depend on your application how many points you want to see in a particular cycle. We just said sample at 30 times the closed loop bandwidth. So now we are saying in hertz, we're sampling at 25 hertz, we're going to be able to see a lot of that wiggling around. We're not just going to see 2 points that the Nyquist would give us on some cycle of oscillation. And the closed loop bandwidth is roughly the highest frequency in our system. So we're wanting to see a lot of that shaking that's going on, or a lot of that waveform. That's why we're sampling much larger than the Nyquist frequency. So now what we're wanting to do, the question I think is, why do we need to sample so much, I think? Because you're saying we can recover the information. Well, we're doing more in a controls setting, more than just recovering information. We're actually trying to manipulate the behavior of the system. We're trying to control that signal, and we may want to do it finer than just at 2 points on one cycle of the oscillation. So that's really sort of where that's coming from. Okay? And we'll probably see that illustrated a little bit more as we go through the class, but for now, I think your rule of thumb is, oh, just sample at 30 times the closed loop bandwidth, and we won't really worry too much more about that decision. Okay? But that's the reason it's there, is because we need more than just the information content in our waveform. Okay? So now let's look at a slightly different issue, and that is now this ability to go back and forth between time domain and frequency domain. Let's now talk about converting. Now that we hopefully understand a little bit more about this z variable, let's talk about converting a time domain linear difference equation into the z domain to obtain a transfer function. Meaning now we are going from the time domain into the frequency domain. Here's our difference equation. Suppose it's now y of n plus a sub 1 y of n minus 1 plus a sub 2 y of n minus 2 plus a sub 3 y of n minus 3 equaling b sub 0 u of n plus b sub 1 u of n minus 1. That's a time domain linear difference equation, and we're not going to specify specific values of those coefficients. Let's just keep them as variables, a1, a2, a3, b0, and b1. The notation that we will use is, let's go ahead and say we're going to be using that the z transform of the time domain signal, little y of n, we will represent as capital Y of z. That's like the Laplace transform. Instead of this script L, now we're using a script Z for converting time domain into the frequency domain. If that's what capital Y of z looks like, then what happens if we take the Z transform, wow, of y of n minus 1? What's that going to look like? That's just going to be a scaled version of capital Y of z. where the scaling amount is -1. Now, you might realize that depending on my mood, I might write y of little n minus 1, or I might write y of n minus 1 capital T. It's the same. In the top one, I'm suppressing the sample period. I'm not explicitly showing it, and other times I might. So I might, in the earlier, I might have written little y of nt. Same thing. Sometimes I will suppress capital T, and sometimes I won't. Hopefully that won't confuse you. If this is the agreed on notation, let's now z-transform this difference equation. And that's not hard, is it? Using this notation. Little y of n becomes capital Y of z. A1 y of n minus 1 becomes A1 z to the minus 1 capital Y of z, etc. Meaning now we can write y of z plus a sub 1 z to the minus 1 y of z plus a sub 2 z to the minus 2 y of z. That was a delay of 2 sample periods, plus a sub 3 z to the minus 3 y of z is equal to b sub 0 u of z plus b sub 1 z to the minus 1 u of z. If we combine all of those or factor out y's and u's from both expressions, we now have 1 plus a1 z to the minus 1 plus a sub 2 z to the minus 2 plus a sub 3 z to the minus 3 capital Y of z is equal to b sub 0 plus b1 z to the minus 1 u of z. And now we essentially have our transfer function associated with that difference equation. We simply take the ratio of capital Y over capital U, and we end up with b sub 0 plus b1 z to the minus 1 over 1 plus a1 z to the minus 1 plus a sub 2 z to the minus 2 plus a sub 3 z to the minus 3. Now, you may get a little bit nervous or anxious seeing that written in terms of z to the minus 1s. But you could factor out a z to the minus 3 from the denominator and the same z to the minus 3 in the numerator, and now you have things written in terms of positive exponents in z. Meaning this could now be rewritten as b sub 0 z cubed plus b1 z squared all over z cubed plus a1 z squared plus a sub 2z plus a sub 3. And that's an equivalent transfer function for that system modeling that difference equation, that third order difference equation. You now have 3 poles. What do you know about the numerator? What can you tell me about the zeros of this system? You have a couple of them stuck at the origin, don't you? You could factor out a z squared from the numerator. You now have a z squared times the quantity b sub 0 z plus b1. You could find the other one in terms of b1 and b0. The bottom, you would have to be told what these a's are, but you have 3 poles in the denominator. Questions on that? And now you should be able to go the other way. If I gave you this transfer function, could you generate a difference equation in the time domain? If I gave you the bottom, green, you might actually want to factor out a z cubed from the denominator and the numerator to get your things in terms of z to the minus 1. Then you're thinking in terms of delays instead of advances. And you could then cross-multiply and go back into the time domain to obtain a difference equation based on a frequency domain model of your system. Now, we said that we had a script z, the z transform. Let's actually define that now. Let's define the z transform, and again, just as a reminder, we can remember the Laplace transform is capital X of s is equal to this integral from 0 to infinity of x of t e to the minus st dt, where you might see this called some kernel, and it's actually weighting, or it weights, all of this time domain waveform x of t. That's an integral because x is true for all time. So we're basically summing up this product of x with this complex exponential e to the st over all time from 0 to infinity. We'll do the same thing, except now in discrete time we just have things defined at integer multiples of our time axis. 1, 2, 3, or capital T, capital 2t, capital 3t. We don't have an integral, now we have a sum. And we can look at two different kinds of z transforms. But the idea is the same. We take our time domain waveform, little x of n, we weight it by some complex number, which will be z is a complex number. Let's just scale it by z to the minus n. Instead of integrating, now we sum from n equals 0 to infinity. This is now our one z transform. We can call this the one-sided because we're only interested in values of our time domain waveform, little x of n, when n is non-negative, or n greater than or equal to 0. If somebody said, well, I have a waveform that's non-zero for negative t or negative time and positive time, then you could also define another z transform that's two-sided. Structurally, it's the same, except now you're summing the negative tail and the positive tail. And this we call now a two-sided z transform. If that's the definition, let's look at some z transforms of some common waveforms. Unit pulse. This is a little different than the unit impulse. What was the amplitude of the unit impulse? Infinite, wasn't it? But what was the area underneath that impulse? 1. Now in discrete time we have a unit pulse. Let me call this, since this is our A signal, let's say this is x sub A of n. This now is maybe a little more believable. It has now a value of 1 right at n equals 0, and it's 0 everywhere else. If I ask you to sketch that time domain waveform on an exam, could you maybe succeed? The answer is yes. What would this look like if we were sketching the unit pulse? Let me make sure and get all these numbers on here. That's it, isn't it? It's just 1 at time n equals 0, and it's 0 everywhere else. It's just a bump. It's a unit pulse, and it happens right at time n equals 0. We want to know, what does this look like in the frequency domain? What's the z transform of this time domain waveform? We can apply the definition. This will be capital X sub A of z. That's this infinite sum from 0 to infinity of x sub A of n weighted by z to the minus n, where z is a complex number. If we simply put on our blinders and just start going, we have x sub A of 0 times z to the minus 0 plus x sub A at time 1, z to the minus 1, plus x sub A at time 2, z to the minus 2, just keep going. But what is x sub A at time 1? 0, wasn't it? X sub A at time 2, 0. What was x sub A at 0? 1. What's z to the minus 0? The unit pulse, z transform, is just 1. That's pretty easy, isn't it? So it's 1 for all z's, all values of z. Capital X sub A of z. Well, maybe that was too boring. Let's look at something else. But before we look at something else, let's remind ourselves of what we can hopefully remember from the continuous time case. Suppose I said, what if we had this unit step, u of t, in the continuous time? So this is sort of going back to 320. In terms of a waveform, there's not supposed to be a wiggle on that, but there's u of t in the time domain. What's the Laplace transform of that unit step waveform? What's u of s? What's the Laplace transform of a unit step? Do we remember? If I said, oh, here's an input voltage and it's the unit step, take this into the S domain and give me the S domain circuit, what would you replace that voltage with? the unit step. It's 1 over s, isn't it? Pretty easy. That's what I'm hoping that you remembered. But this is 1 over s. What's the pole zero diagram look like in the s-plane then? Where's that pole? It's right at the origin, isn't it? This is now the pole zero diagram. There is no finite zero. There's no finite value of s that causes capital U of s to vanish. That's now the unit step in continuous time. Let's look at what happens if we had the unit step in a discrete time setting. This is now our second, or our B waveform. Here's our unit step. What does that look like as a waveform? What's x sub b of n? 1, 1, 1, 1, 1, right? Pretty boring. And it just keeps going and going. We could then define that to be x sub b of n is equal to 1 for all n greater than or equal to 0. We want to know what's that look like in the, what's its z transform? What's the z transform of that unit step? By definition, that's this sum from n equal minus infinity to infinity. We'll just go ahead and say that two-sided. It doesn't really matter because x sub b of n is only one-sided, isn't it? Can we simplify that expression, that argument, or that, yes, the argument of the sum? Does that simplify at all based on what you know little x sub b of n is equal to? We can replace that time-dependent waveform x sub b of n with 1. It's always 1 for every value of n, except those negative n's, it's not equal to 1. So we can now rewrite this and say from n equals 0 to infinity, this is 1 times z to the minus n. This now becomes z to the 0, which is 1, plus z to the minus 1 plus z to the minus 2 plus z to the minus 3, and it just keeps going and going. Maybe that doesn't look very nice. Our unit step in the s-plane was 1 over s, wasn't it? We had a closed form, we had a ratio of polynomials in s for capital U of s. This looks like an infinite sum. Well, we can find a closed form expression for that. Using our strategy that we've looked at before. When is x sub b of z going to be well behaved? When will this even make sense to have this infinite sum of all these z's? Z to the minus 4, z to the minus 5, z to the minus 6. If we keep adding those up, when is that going to make sense, or when will it be a bounded value? That infinite sum, when will it be bounded? We're adding 1 plus z to the minus 1 plus z to the minus 2. There's a common ratio, isn't there, in those terms? Z to the minus 1. First it's raised to the zeroth power, then to the first power, then to the second power, then to the third power. So if that z to the minus 1, which we keep raising to higher and higher powers, if we kept that less than 1, this would be good, wouldn't it? It would be fine. That sum would converge to a finite value. Meaning, we could actually make sense of capital X sub b of z, which is 1 plus z to the minus 1 plus z to the minus 2. That's well behaved or nice. You could think of this as z to the minus 1, 1, z to the minus 1, 2, z to the minus 1 cubed. This would be nice or well behaved. As long as that z to the minus 1 is less than 1. As long as it's less than 1, that's going to be collapsing. And as we raise it to higher and higher powers, that's going to vanish, and so that infinite sum will converge to a finite value. To determine what that finite value is, now we do our sort of strategy that we learned last time. What if I scale both sides by z to the minus 1? I now have 1 times z to the minus 1, and let me write it over here. Then I have z to the minus 1 times z to the minus 1. That's z squared. The tail looks exactly the same, doesn't it? It's infinitely long, so that's fine. Now I can compare the black and the blue. I can subtract them. So if I take the blue away from the black, what do I have on the left-hand side? Right? I have capital X of z minus z to the minus 1 capital X of z. What's on the right-hand side if I subtract the blue from the black? The tail all goes away, and I'm just left with 1. Now I know, or now I have capital X of z, capital X sub b of z is now equal to 1 over 1 minus z to the minus 1. When? When is that true? When it's nice, when it's well behaved, when this z to the minus 1 is less than 1. Or we might say that this converges, that infinite sum converges as long as that term that kept getting raised to higher and higher powers, that factor, which was z to the minus 1, was less than 1. Well, this is just 1 over z is less than 1, or that's now the absolute value of z is bigger than 1. And maybe you don't like writing things in terms of powers of z with negative exponents. We can either multiply both top and bottom by z or factor out a z to the minus 1 and cancel things. But you can see, I hope, that capital X sub b of z, this is the z transform of a unit step in discrete time, is now z over z minus 1. As long as z is outside of 1, or the absolute value of z is bigger than 1. And we actually have a picture for that. And an expression. The z transform of a unit step is this z over z minus 1, but we it's true as long as wow. You can use a compass and make a better circle than that. But this is true as long as z is bigger or lies outside the unit circle. It has an absolute value. This is our z-plane. That transform of z over z minus 1 is now, it exists as long as z is out here outside of the unit circle, and we call that region where it converges the region of convergence. The region of convergence for the unit step in discrete time is this unbounded region outside the unit circle, and where are the poles and zeros of that transformed or frequency domain representation of the unit step. Do we have any finite zeros? And we have a pole at 1. How does that compare to this pole zero diagram there? That's in the S-plane. S is equal to 0. Where does S equal to 0 map to in the Z-plane? Z is equal to e to the st. S equal to 0 gives us z equal to 1. So that pole at 1 is consistent with this pole at the origin. It's just we've now introduced a little bit different pole and zero diagram. Now we've introduced a finite zero, but it's consistent with what we were seeing in the S-plane. Now we have this pole at 1 in the Z-plane, and that's consistent with the pole at the origin in the S-plane. What if you now had a different waveform? An exponential. What's an exponential look like in the discrete time setting? Do you believe me? Is that an exponential? Can you picture what that looks like as a time sequence? And if you can't, pick a particular value for R. Select a specific number for R. R equal 1/2. Now it's 1/2, 1/4, 1/8, etc. What if R was 2? It's 1, 2, 4, 8. Exponential, isn't it? It's a growing exponential. The other one was a decaying exponential. But they both are exponential waveforms. What do you think? Well, how does that relate to what you already know? How does that compare with this x sub c of t? Well, let me not call it c. Let me just say x of t equal to e to the, that's an exponential in continuous time. If we wanted discrete time, what are we doing? Well, we're sampling little t. We're dicing it up. We now have x of t with t replaced with little n capital T, so that this is now e to the minus a little nt, but that's now just e to the minus a nt, e to the minus ant. But you can think of this now as x of nt. This is now e to the minus at raised to the n. What's e to the minus at? That's just some r to the n. That's what we said we were dealing with in discrete time. And there's the connection. We'll pick up next time with trying to find the z-transform of the exponential, the exponentially damped sine and cosine, etc. Don't forget homework 1.